All right, let's get right into it. We've got to talk about this paradox that is driving developers nuts. We're living in this amazing era of edge computing, right? Apps are supposed to be instantaneous. So why do they still feel so sluggish sometimes? Well, the answer isn't hiding in your code. It's actually all about the physics of your data.
I mean, this is the question, isn't it? You've done everything right. You've pushed your code out to this incredible global network, so it's just milliseconds away from all your users. And yet, the experience can still feel laggy. It's frustrating. But here's the thing, it's not your fault. The real bottleneck, the real villain in this story, is hiding somewhere you might not expect.
And that brings us right to the heart of the issue. It all comes down to this fundamental conflict. It's like a clash of two different worlds, a major disconnect between where your application logic lives and where your data lives. So, on one side, you have your code. And thanks to these absolutely amazing platforms, like Vercel, Cloudflare, the whole crew, your application logic basically lives everywhere at once. A user in Sydney visits your site, boom, they hit a server in Sydney. A user in London, they hit a server in London. That's the magic of the edge, and it has totally changed the game for building on the web.
But, and this is a huge but, here's the catch. While your code became this globe-trotting world traveler, your data, it pretty much stayed home. Yep, most traditional databases are still just sitting in a single centralized cloud region. You know the one I'm talking about, good old US East 1 in Northern Virginia. And that physical distance, oh man, that creates a massive problem.
Think about it. That user in Sydney gets your website's code almost instantly from the local edge server. Fantastic. But the second that code needs to fetch some data, it has to make a trip all the way across the Pacific to Virginia and all the way back. We're talking about a 250 millisecond round trip. In the world of web performance, that's an eternity. That one little data fetch completely wipes out all the incredible speed you gained from being on the edge in the first place. This whole phenomenon actually has a name. It's called data gravity, and it's such a perfect term, right? The idea is that data has mass. It's heavy, it's a pain to move, and it has this natural gravitational pull that sucks applications and services towards it. For years, the solution was simple. We just moved our code to be close to the data. But now, with the edge, we're trying to do the exact opposite, and it's causing this cosmic collision.
Okay, but listen, as bad as that latency penalty is, it's literally only half the story. The problem goes from bad to catastrophic the moment we bring serverless functions into the picture. Seriously, this isn't just about your app being a little slow anymore. This is about whether your app can even stay online.
So let me paint you a picture of how a complete meltdown happens. First, you get a sudden spike in users. Maybe you went viral. Awesome, right? Well, that spike causes thousands of serverless functions to spin up all at once. Now, every single one of those functions tries to open a new connection to your database. But here's the thing. Your traditional database was only built to handle maybe a few hundred connections, max. The result? It gets totally overwhelmed, runs out of connections, and just falls over. Game over. And this quote just says it all, doesn't it? This is not a performance degradation, it is a complete service outage. Let that sink in for a second. We're not talking about a slow loading page, we're talking about your entire service going dark, taken down by the very serverless architecture that was supposed to give you infinite scale. The irony is just painful. So, okay, deep breaths. How do we fix this mess? How do we possibly bridge this massive gap? Well, it was this exact crisis that forced a change. It led to a whole new wave of databases, a new generation built from the ground up with a single purpose: to not just survive in a serverless edge-first world, but to actually thrive in it. Now, when you hear the term serverless database, your mind might immediately go to pay for what you use pricing. And yeah, that's part of it. But that's not the real magic. The real innovation here is architectural. It's a completely new design, engineered specifically to solve that connection catastrophe we just walked through. And at the center of this new architecture is our hero, the connection proxy. Honestly, just think of it as a brilliant traffic controller for your data. It stands right in the middle, between those thousands of frantic, short-lived serverless functions on one side and your calm, steady database on the other. It wrangles all those incoming requests and funnels them efficiently through a small, pre-warmed pool of connections. It's the missing piece. It's what makes the whole system work without blowing up. And what's so cool is that this new architecture doesn't just stop outages. It actually unlocks some incredible new superpowers for developers. I mean, just imagine being able to branch your production database the same way you branch your code with Git.
Or what about spinning up an instant perfect clone for testing in seconds? This isn't science fiction anymore. This is what platforms like PlanetScale and Neon are making possible today.
All right, so this whole new serverless database world has basically split into a few different paths, a few distinct philosophies for how to solve this data problem. And what's interesting is, it turns out there's no single right answer. It's more about different approaches that are optimized for different kinds of problems.
So let's look at a couple of the big ones. On one hand, you've got a platform like PlanetScale, which is all about something called horizontal sharding. The easiest way to think about it is like splitting a massive phone book into smaller, more manageable volumes. A through M in one book, N through Z in another. It's a battle-tested technique that was born at YouTube to handle just insane scale. Then, on the other hand, you have a company like Neon. Their whole philosophy is about separating the storage of your data from the compute power that queries it. This is really clever because it lets you scale each part independently. You can even scale the compute all the way down to 0 when you're not using it, which can save a ton of money.
And then there's a third philosophy, which is just fascinating. It's being championed by a company called Turso, and their approach is totally different. Instead of trying to manage access to one central database, they just said, what if we replicate the entire database? So they create copies in dozens of edge locations all around the world, putting the data physically right next to your code and your users.
Okay, so let's break this down a bit and look at the trade-offs. PlanetScale, built on Vitess, is essentially supercharged MySQL. It's an absolute beast for massively scalable applications with a ton of transactions, what we call OLTP. Think e-commerce or social media. Neon, on the other hand, is laser-focused on giving you a top-tier, cost-effective, serverless version of PostgreSQL, which is, one of the most beloved databases on the planet. And then you have Turso, using a fork of SQLite called libSQL. Their sweet spot is read-heavy applications that demand the absolute lowest possible latency. By putting a replica of your data right at the edge, they can get read times down to sub-millisecond levels. It's unbelievably fast.
So when you step back and look at all this, what's really going on? Well, these modern platforms aren't just inventing clever new tricks out of thin air. What they're actually doing is providing new, modern answers to some of the oldest and most fundamental questions in all of computer science. And right at the heart of all this is something called the CAP theorem. It's basically a foundational law for any system that's spread out across multiple computers. And it says something very simple but very profound. You can't have everything. You have 3 things you want: consistency, so everyone sees the same data; availability, so your system is always online; and partition tolerance, so it keeps working even if parts of the network fail. The theorem says you can only pick 2.
But here's where it gets really cool. Modern systems like Turso show us that it's not always a harsh binary choice. They make these really intelligent, nuanced trade-offs. For example, when you write new data, it goes to one primary central database. That guarantees strong consistency. The write is confirmed, and everyone will see that exact same version of the data. But when you read data, you're hitting those super fast edge replicas. They're what's called eventually consistent, which just means they might be a few milliseconds behind the absolute latest write. But what do you get in exchange for that tiny delay? You get blindingly fast reads and incredible availability. It's just a brilliant, practical solution to a decades-old theoretical problem. And that brings us right back to where we started. The revolution of edge computing literally forced a revolution in how we think about data. We've untethered our code, right? We've let it run free all over the globe. And so the question that these new databases are forcing us all to ask is a really powerful one. If your code can now live anywhere, shouldn't your data be able to as well?